What I'd like to consider in two problems that we're going to work through in this session uh, is conditional probability, which I'm working on a premise. Some starting point is that you have done questions on conditional probability already. You have some experience with it. It might not have been called conditional probability, but the key word which created the condition would have been this idea of without replacement or not replaced. Because when in these situations where you have counters in a bag or balls in a bag, if you don't replace one, then what happens the second time is conditional on what happens the first time. There's a condition. So that's the kind of question we want to explore. We want to, and I want to make that link between tree diagrams, the use of the tree diagram, and the use of set notation. So bringing those ideas together, so when problems like this come up later on, and potentially in an exam, you might be writing, you're well equipped to manage it. So that interplay between conditional probability, or a conditional probability being represented by a tree diagram, or using and or probability language notation, and what it means in terms of set notation. We sort of want to tie those ideas up together. Now, because you have experience with set notation, that's the starting point. You should have gone through the work with set notation, and you should have also had experience with working with tree diagrams. I'll ask you to have a go at doing this question and see if you can marry those two ideas together. So off you go, you try the problem. And then I'm going to do it, and obviously as I work through it, if it is that you didn't do all of it or you were stuck, then hopefully I'll unstick you and you can finish it successfully, doing a lot of the work on your own or for yourself, taking that ownership. So off you go, try to solve the problem. Pause, and you're working on the problem. So now let me get started on the problem, and I will give you enough opportunities to stop me and to continue where I left off if you needed that start, shall we say. The bag, we have a situation with a bag with 9 red counters. I should put that in red, so I'll just swap over to red. 9 red counters, and then there are 7 green counters. The counter being selected at random, and there's an interesting situation here where if it's green, it's replaced. So green, it is replaced, but then if it is red, it is not replaced. The red is not replaced. The first thing we want to do, let's build a model. Let's build a tree diagram, and then we can use that to answer the questions. I will be clear, it's not absolutely necessary to draw a tree diagram for this question, but I do think that a tree diagram would help. And it also helps me make that link between the tree diagram, the branches, and what each branch, what a combination of branches represents when it comes to probability and set notation. In total, it was 9 red and 7 green. So in total, we have 16 counters. 16 counters. So the denominator in this question, for all our fractions, we're starting off with a denominator of 16. And there's one other bit that I can't do the model. I just realized it because it didn't talk about how many times you pick a counter. But you do get that information when you read down in terms of the second, where they're asking you the questions. We're talking about the second counter. Second, there's no mention of a third counter, so I'm thinking there's a first try and a second try. And let's see, we can get that where you will be able to see. So first try and a second try, that's what we're looking at. So I'll build a tree diagram on that basis. And I'll put the tree diagram as far as possible to the right, giving me more space. Actually, no, I'll put it on the left. Choice. Yeah, no, right. There's a reason for it. I knew there was a reason initially, so I'll put it on the right. Let's get that sorted. Great. Okay. So for the first try, we can either get a red or a green, and a similar thing happening the second time around. It's either going to be red or it's going to be green. And I need to make that a lot bigger, don't I? Or it's not going to fit. Ooh la 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 la. That's why I could edit all these things, to be honest, but that spoils the interaction and the natural. What I'm trying to do is simulate what would probably happen in the classroom. So first time it can be red or it can be green. And then the second time around we can get the red or the green or the red or the green. And yes, you're probably thinking, hey, sir, why are you not putting the green in green? And hey, we don't have all day. Come on, come on, come on. Gonna need a bit of space for the combinations, won't I? Right, so the probability of red the first time getting red, well, there's 9 red counters and 16 in total. So the chance of getting red is 9 on 16. Now the second time red, and this is where it gets really interesting because it says if it is red, it is not replaced. Not replaced means that, okay, I took out a red. I no longer have 9 red because I've taken out 1. I now have 8 red. And I no longer have 16 counters because if I took a counter out the first time, I now have 15 counters. So the chance of getting red the second time around will be 8 on 15. Similarly for green, you took out 1 counter. If it's red, it's not replaced. So the chance, the denominator is 15. There's still 7 green because the first one was red, so it's 7 on 15. 7 on 15. And we can finish the diagram. Green is going to work a bit differently because if it's green, it is replaced. So the chance of getting green the first time will be 7 on 16. But then when it comes to getting green the second time, I already took out a green, so I now have 6 left, but it's 6 on 16. In terms of red, we didn't take out any of the red. It's still 9, but because we replaced, it's going to be 9 on 16. So you can see the difference there in terms of second time around. For red, there's no replacement. For red, there's no replacement, so the denominator reduces to 15. If it's green first time, no change, so the denominator remains the same. Now, the question is, the second counter is red given. It uses the word given. Given that the first counter was red. So what's the chance the second one is red given the first one is red? So we're thinking about this branch here. This is the branch we're thinking about. I'll just circle it. That's the branch we're thinking about. Red and red. Red, red. Okay, but there's a difference in our logic here to answer the question. Now, they use the word given, and what should trigger from your work in set notation and probability already is when we use the word given, we're thinking about conditional probability. So we're thinking what we want to find, this question in terms of set notation, what I want is the probability of red, and I'll put red 2 just for clarity here. And that means I'll have to change all my notation. Red 1, red 2, green 1, green. We'll just put 2s, 2s, and 1s, okay? So what we want is the probability of red 2, given that we had, and why am I writing it in, oh boy, in green? That is creating a problem there, yay. Right, the probability, what we want is the probability of red 2, given that we have red 1. That's what we want. Question is, where is that in the diagram? I'll confirm to you that, well, that calculation, we've already done that calculation. Recall that if when we go to that RR that I put there, that's the probability of when we follow the branches and you do multiplication, which is what you're used to doing, that's actually the probability of red intersection red. And if I change the notation, make sure I get the notation right, red 1 intersection red 2. That's what that probability is when you do the multiplication, red 1 and red 2. So, well, where's the conditional probability? Well, the answer is going to be the 8 on 15. The answer is 8 on 15. That's the probability we're looking for. And the reason that is the answer, let's just think about what we're doing here for a moment, and let me just make this a bit clearer for you. Just put a blue line down there. And a straight line will make it a lot lovelier. So we'll get a straight blue line there. Brilliant. Right, so we got the 8 on 15. And what is that indicating? And that's the big point I wanted to get across, is that the 8 on 15, this second branch, the second time we put the red, that branch represents the conditional probability. When you do red the second time, and we're working on this second branch, the representation for this is set notation. This is the probability of red 2, given that I had red 1. The representation, that's 7 on 15. What does that 7 on 15 represent? That 7 on 15 represents the probability of getting green as your second pick, given that you got red the first time. G2 given red. That's what it represents. So if that was the question, I'll just put that in there. And make a note of this. It's really important that you understand where the conditional probability lies in the tree diagram. That is very important. And that way you can use the diagram better. Or accurately is a more appropriate term. So in terms of this green, what I'm saying is that this probability here, that's 7 on 15. I'm just thinking about how do I represent this clearly. I'm going to draw this down here. What am I saying? If I have red 1, and then green 1, and then we have red 1 again, and the green 1, what I'm saying and what I'm trying to get across is that the first probability is the probability of red. The second probability is the probability, and we need to put into 2s. I put 1s, but I should have put in 2s, so we'll put 2s there. 2, 2. Well, the probability, the second probability, so that's the probability of red 1. Probability of red 1, that's being represented by 9 on 16. And then the probability of getting red 2, given that you got red 1, that is what's being represented by 8 on 15. This probability branch here, which is 7 on 15 in the diagram, is the probability of green the second time, given that you got red the first time. So the second branch is getting that second probability, given that you got the first branch. That's the idea I want to get across here, and hopefully that makes sense. Once you got that, then that's the big link between set notation and tree diagrams. Okay, we have the answer, and by virtue of what I'm putting forward, it means that we just had to read off the value 8 on 15. So I'll pause there. You have a chance to take that in if you, okay. And I think I've eventually got there, and it should be clear. Okay, that idea. Right. There's one more link I want to make with this before we actually answer the rest of the questions, because it's important that I make the links. And I'll just do a copy of this diagram to do that. So copy, paste, right. And I will also, I'll delete. I'm just thinking about clarity here. So I'm going to delete the second branch of the tree. We'll come back. We'll get it after. Okay. So we have that explanation that these are the conditional probabilities: red 2 given red 1, green 2 given red 1. Let's just look at the link between. So I'm going to just extend here and just make that link between the conditional probabilities and the fact that the resultant probability, recall, what do we get if I do red 1 multiplied? What is this saying? Because remember, if I told you I wanted the probability of red 1 and red 2, well, what you will tell me that is I will have to multiply the two branches, the probabilities on the two branches. And what you see there is that means that the probability of red 1 and red 2 is equal to the probability of red 1 by the probability of multiplied by the probability of red 1, red 2 given red 1. That's the probability of getting there. Probability of red 1 intersection red 2 is the probability of red 1 multiplied by the probability of red 2 given red 1. And on the basis of that, if we rearrange, you will see the conditional formula for conditional probability. The probability of red 2 given red 1 is the probability of red 1 intersection red 2, so the probability that's currently on the left-hand side, divided by the probability of red 1. Okay, the red 1 that we're multiplying on the right, we have to divide on the left. And that's the really, really important bit I wanted to get across. It's not absolutely necessary to use those techniques in this particular question, but it's an opportunity for me to show it to you. And there will be questions. It doesn't come up a lot, but it could come up in your exam. So I thought it was important to go off and demonstrate that. And then we'll come and finish off the specific question. So that's the link between conditional probability use the set notation and your tree diagram. Let's go back and finish our job, the actual job we have to do here. And I will go back to my previous question, the previous working I had. And what do we want? We found the second counter, given that the first counter is red. So that conditional probability, we've been able to read it off on the direct diagram. It's 8 on 15. Now the second problem is asking us, what's the probability of the second counter being red? Let me get some space and work on that one. So we want the second counter red. That's what we're concerned about, the second counter being red. Now from the diagram, you should identify that there's two ways for the second counter to be red. It's either you're getting the red, so we're following that pathway, red, or the alternative is that it's green first and then red. So red, or green, red. Red and multiplying, green, red, or so green, red, and multiply, and then because it's red, or green, red, we have to add up those two probabilities, the products of those two branches. So to do that one, I will rub off all that probability notation, that set notation. I'll take all of it off, and I'll just write out the calculation that we need to do. So what do we want? And because I want you to be comfortable with set notation, to improve that, I'm just going to write it out using set notation. So for B, you don't have to do this, but I want you to see it. So if you have a question that leans more to using set notation, you can make the link between the two. So what do we want? We want the probability of red first time and red the second time. That's one way of getting red the second time. Red first time and red the second time. So red first time and second time. Or the other option we want, and I'll put it in here in terms of the diagram, is getting green first and then red, because remember it's red the second time. So probability of G1 and red 2. So that's what we need to add, plus the probability of G1 intersection R2. Intersection can be used, means the word and. And what does that imply? Now, and again, you'll do 9 times 16, 9 16ths times 8 on 8 15ths plus 7 16ths times 9 16ths. That's what you're going to do. But I want to stick into probability notation so you can see the links. Set notation, and then we'll reduce to the fractions. We'll get the answer. The bigger picture here is not just getting the answer, it's understanding set notation. That's a skill we want to develop so we can move between the two. And the link I want to show you is that the probability of red 1 intersection red 2 is actually probability of red 1, getting red 1, multiply that 8 on 15, well that's the probability of getting red 2, given that you got red 1. So that's the change we've made there. And then we want to add to that the probability of G1 intersection R2. And what that is the probability of getting G1. That should be a P. So probability of getting the green the first time, probability of getting the green the first time, 7 on 16, multiply by the probability of getting red the second time, given that you got green the first time. So times probability of red the second time, given that we had green the first time. We now have everything written nicely in set notation. And I have to say it, this is not necessary, but I'm doing it to show you those links between the tree diagram, conditional probability, the additional conditional probability formula, because I'll be honest with you, at this stage it's difficult to find questions that force you to use the set notation, but that could come. And you need to be able to switch between the symbolic, the set notation, and then what we're going to do now to the specific numeric context, in which this case probability of red 1 is 9 on 16. So 9 on 16 multiplied by the probability of getting red 2, given that you got red 1, which is 8 on 15, so times 8 on 15. And then we want to add on to that the probability of getting G1, which is 7 on 16, multiplied by the probability of getting red 2, given that you got G1, which is 9 on 16. And you will work that calculation out on a calculator. The figure you should get when you work through that, 2097 on 3,840 is what I have there as the answer to the calculation. Now, so that's what you're looking at there. And there you have that link between your for your probability. The intersection is the same thing as the first probability, R1, multiplied by the condition, R2, given R1. That's a big link that you want to be aware of and to be comfortable to use. Let us finish off the last part of the problem. Let us do C. Let's do C. Or before I continue with that, this number, as I think it's if you have your answer as a decimal, that's fine. I believe it's 0.54. You do the division and you just double check that this fraction is the same as your decimal. It should be, so that should be fine. Let's look at doing part C now. Part C, so I need a bit more space. Gonna clear to get part C. We're gonna erase. Okay, we have the tree diagram, so that's sufficient there. And have a go. Write part C using set notation. Again, not part of the question, but new question. Write out C using set notation. What are we looking for? The two counters are of, you have a chance, power the pause, and you work through it. Use the right set notation and then do your calculations. The two counters are different colors. Different colors, well, we already have one situation of different colors. We already have the green and red. The other combination that will give us different colors is if we got red first and then green second. So what we're interested in next is the probability of getting red first and then getting green second. So for C, in terms of set notation, what we want for C is the probability of red first and then green, or the probability, so we're going to add plus the probability of green first and red second. That's the two different ways you can get two counters of different colors. Switching to what do we multiply, that's the good, this is going to be, and I can just work it out using set notation now, probability of getting, I keep writing R instead of P, so the probability of getting red first multiply by the probability of getting green given that I got red first. That's what the notation means. And then I have to add on or the other way, so add or the probability of getting green first multiply by the probability of getting red second given that I got green first. Doesn't it make sense when you read it out and the notation? So we're talking, hopefully I was talking clear English there, but I'm writing set notation. And now that I know my probabilities, I can write them out. The probability of getting red first was 9 on 16, and then the probability of getting green second, given that I got red first, is 7 on 15. So I need to multiply by 7 on 15, and then I need to add the probability we had already, probability of getting green first, which is 7 on 16. And we need to multiply that by the chance of getting red the second time, given that I got the green first, which is 9 on 16. And that's the multiplication we have there. That's what you want to work out. And doing that one, you should get 1,953 on 3,840. So yes, I did do the calculation before. I don't want to, don't need to worry about that too much. Method is what we're interested in. Answers follow if we use right methods and strategies. Make sense? Sort of, maybe. Oh, yes, sir, got it. I'm just, and do not think we're doing too much work. And it's really important that we start moving away from thinking we just want to get the answer. What do we need to be developing our understanding of the different concepts and making connections that are not really necessarily made in the textbooks that we might use, or in they're not really made explicit all the time, but we need to be able to make those connections because there might be some non-routine, unfamiliar questions that we have to solve in future, and understanding concepts like this could potentially help and make the difference in your grade, or when you start doing something mathematical, engineering, etc. at university can make a very big difference. Let's explore this problem. Well, actually, not let's. You do it. You explore it. You do it. Have a go. You're an expert now. Make it happen. And the thing I will ask you to do, however, is to use as much set notation as possible. Immerse yourself in the usage of set notation, and switch from set notation to the visual if you need a bit of a tree diagram, etc. as necessary, just so that you can really take ownership and make those links between the set notation, the language, and the problem, etc. The more practice you do that, to deepen your understanding of conditions and how conditions are represented visually and symbolically, and also systematically using listing. I'm going to start off with doing some listing on this. So let's just explore that whole interplay. You do as much as that to get the answers. Off you go. And you have the power to pause. You've worked on it. I'm going to start working on it. And as usual, you can stop me at any point. You are in control of me. That's the power of video, to go further as necessary. So, right. Reading through the question. Very little information presented, but gets some interesting calculations for us to do. We have 11 red, and we have 8 black. So 11 and 8, 19. We're thinking there's 19 of these balls in total. And then the other key piece of information, we're open-ended. Balls are really removed from random. So it could be 1, 2, 3, 4. It can go on and on and on. Scanning through the text, however, we're thinking about the second ball removed in part A and B, and then in part C, the third ball removed. That's interesting. But critical in terms of the information to build on model is without replacement. We're never replacing a ball when it comes out. 19. Second time will be 18, third time 17. So that's in your mind as well. Now let's model this thing. And I'm going to go with a listing strategy first. So I'm thinking, right, how can this go down? I can get red first and then get a red again. Or I can get red first, and after I get the red, I can get a black. Then the other way is I can get the black first. That can happen. Two different ways. Getting black first, and the second time getting a red the second time, or I can get a black the second time. Those are the 4 outcomes that can happen with two picks. Okay. Now, the question is A. Let's focus on A now. A is asking me, the second ball is black, given that the first ball is black. And I think the issue that can come up here is second ball being black. Quite quickly, a lot of people will dive in, and for A, they'll just talk about probability black and black, or which is the same thing as writing probability of black intersection black, black first time and black second time. So if you want to use the short form for your set note, for your probability notation, that's fine in this context. That's fine. Just making sure you're aware that black, if we don't put any symbol, it means intersection, it means and, it means to multiply. Okay, that's the idea I wanted to get across there. And a lot of people dive in and think that's what the problem is asking, and then they'll just multiply 11 on 19. That's a chance of getting black the first time, not 11 on 19. What am I saying? There's 8 black. So 8 on 19 the first time, and then the second time it's not being replaced, so there's 18 the second time, and well, then there's 7 black, so 7 on 18. So 8 on 19 by 7 on 18. That's what I think a lot of people go for, because that's a typical question that you've been used to be doing, and but it's wrong. It's wrong. It hasn't answered this question. Our question is not given. That question is not asking for black intersection black. That question is asking for the conditional probability. It's asking for the given that the first ball is black. What the question is asking you to do, so let's just put an X. This is wrong. Question A is asking you for the probability of the second ball being black, given, line going down, that the first ball is black. That's what the question is asking you for. And that, well, you can start writing formulas and all of that to try and work through it, but it's like, hang on, let's switch. We have a list. Doesn't really tell us how to get black given that black one, but we can either think about it logically, or to really make it simple, just quickly draw the first parts of a tree diagram. And then we can stick with logic after, because The answer is going to be 7 on 18. I'll tell you what the answer is. The answer is just the 7 on 18, nothing else. Why is that the answer? And now I can remove the piece that I was, the incorrect bit. I'll just remove that. Whoa, whoa, whoa. Didn't want to go down that low, but that's fine. I'm going to take this out. Don't need that wrong bit anymore. And what we want now is to show this on visually. Why is the answer 7 on 18? Well, the chance that the first probability that 8 on 18, that's the probability of getting black the first time. Now, given is the second branch. This is what, so given that I got B1 the first time, now I'm working out a probability to get B2. So the condition, the probability for the condition goes in here, and the condition is that I got B1 the first time. The first branch was B1, so the question was asking, A is asking, if the first branch is B1, what's the chance the second branch is B2? That's what it means in terms of the tree diagram. And, well, it's 7 on 18, because if there's no replacement, without replacement, then we now have 17 left. We only have 17 balls, and if the first one was black, there was 8 initially, 1 is out, so we have to have 7, and I put the wrong probabilities. Oh my goodness. You know, I'm thinking about the condition. It's 8 on 19 is the first one. Let's just correct that. Let's correct that. And then the second one, the condition, if 1 is out, there's 18 left, and it's 7 on 18. So that's the key idea. I want to drive that home now. And hopefully we're okay with it. That in terms of conditions, if I'm talking about the second, what's the second color of the second ball given the first ball, what I'm looking at is the probability for the second branch based on what the first branch is. That's what we're asking for, and the answer is 7 on 18. So A, 7 on 18, and let's just make sure A looks like A. Let's make that a bit nicer and neater, okay? Right, so we got that. A, 7 on 18. Now let's think about B. Let's deal with B. I was trying to shift over A, but that's like not gonna happen. Doesn't matter. We can do B here. We got B. And for B, it's the second is black. So to work on B, I'm gonna take a more traditional approach. It's not a conditional probability, so traditional, straightforward approaches would work. Second is black. It's either I get red and then I get black. So this is one possibility for B. And then the other bit, I'll actually just put in the B here and make it clear. So B is second is black, or we could have black and black. Note what I said there, black and black. So red and black, or black and black. What do we want here? We want the probability of red and black, so red one, then black the second time, plus the probability of black the first time and black the second time, because there's 2 different ways that we can end up with black at the end. In this case, what we're doing is multiplying. This is multiplication. These are intersections, so this is red 1 intersection black the second time, and plus black 1. Change my color. I like my color coding. Well, I'm trying to, that's black 1 intersection black 2. We can use that notation interchangeably, and we want to do the multiplication now. So multiplication, chance of getting red the first time, well, red, there's 11, so it's 11 on 19. So I got 11 on 19. Why am I writing in blue when I'm talking about red? What is on with me? 11 on 19. And then the chance of getting black the second time, well, if I got red, there's still 8 black, but there's no replacement, so it's 8 on 18. And then we move on to the second situation, so the second part of the calculation, chance of getting black the first time, there's definitely 8 black the first time, 8 on 19, and we need to multiply that by black the second time, which is 7 on 18. When you do that calculation, you will get what do I have here? 144 on 342. So that's the answer. You should end up following that logic. 144 on 342, which you can check if you've put your answer as a decimal. Again, that's fine. You can double check if that is the same as your decimal. You want to be putting it, I would say, to 4 decimal places. Just do 4 decimal places and you're fine. Now for C. Third ball is black, but with a condition. that the first had to be black. Let's make some space to deal with this. Let's do I'll make a copy so I don't lose what I've done. Yay. Okay, right. So let's deal with this. I'm going to rub off the links to B. Going to get those off. Didn't want that to happen. I'm going to rub off the bit for B. And also, I don't think I need A anymore. So I'm going to take that off and we'll build it from here. Now, the condition, so I got some space here. See, the condition is given that the first ball is black. First ball was black, so the first ball has to be black. What that means is that these branches, the listings with red first, they can go. We're not interested in either of those. We're interested in black first. Okay? And quickly you realize, well, there's two possible ways this could happen, that the third could be black. And I can just put in here black 3, third black, so I'm just putting B3, third black, B3, okay? And what we're seeing is that we want given that the first is black. So what do I want? If I link this up in set notation, what do I want? What do I want? I want the probability of B3, actually no, let me put the second try, red in the second try and black in the third try, given that I had black first. That's what this probability is, B1, then R2, then B first, then R, then B. That's what it is. And then I want to add on, or the probability of B the second time and B the third time, given that I have B the first time. That is what we are looking for. That's what we're looking for. We have that condition. So based on that, the condition, which is reduce the denominator, because think about it. What's happened? All the options, the reds, they're gone. They're gone. We've removed that, so we're reducing our number of options. We're reducing them. So let's work this out. Let's see if we can work this whole thing out. We'll write down the probabilities. Okay, what's the chance of this happening? Well, the first thing you want to write in, and you'll see that actually from a mathematical perspective, the set notation might feel a bit funny. Hopefully you're thinking, oh yeah, that makes sense. I'll clear off these, make myself some more space, and let's get the multiplications going. Because all this is the probability of, in terms of thinking about the branches, it's the probability of the R2, this R2 that we have here, multiplied by the probability of B3. Okay, we only want this R2 and B3, so we need to take into account that B1 has occurred. So what I'm going to go through here, and I'll do it slightly differently. I'm going to go through the story that I had B first. Having B first, I'm building the tree diagram. For me, I think that's a better way to do it. So I'm building it. I had B first. That was my B1, and B1, well, how did I get B1? That was 8 on 19. So the 8 on 19, that's done and dusted. That's not going to feature in my multiplication. But I need to factor that in to get the two numbers that I need to multiply, the two fractions. That's what I'm trying to say. Okay, that's happened. Now, as a result of that happening, hopefully you can understand what I'm saying. As a result of this happening, based on this condition, now what are the two probabilities that I need to multiply? That's what we're trying to get here. Okay, and the first probability is, well, second time getting the red. So R2 in this condition, under this condition, what's the chance of R2? And just for clarification, I've only written down this so I can get my probabilities right. This fraction does not in the calculation. That's the part I'm trying to get home. That can't be in the calculation. That condition has happened. What is my first probability? So it's the first one is black. So R2 under this condition is going to be 11 on 18. Because I already had one ball gone. So 18 is my denominator and there's 11 red. And then the B3, remember, well, I already had a black one. So black is now 7. And well, 18 goes down to 17. I've already taken two balls out. So it's 17 left. that is the fraction. So the probability R2 intersection B3, so the probability of this the sequence of events happening that will give me a black the third time, given that I got black the first time, hopefully that makes sense the way I'm saying it there, is 11 on 18, and I'll put it in red so you can see all we're multiplying is R2 and R3 because we've accounted for that condition already. So it's 11 on 18 multiplied by the 7 on 17. And then for the second probability, which I'm going to have to add, so let me put that plot, or, because now we're thinking about the other way this can happen, or let's work out the second scenario here, and I'll put it down here. So we already have B1, so B1 has happened. Do I have enough space? Yeah, B1. Let me just go up a little bit. Okay, right. So B1 has happened. Got the B1 out of the door, that's the 8 on 19, and I'm just using that 8 on 19 to help me with my counting. It will not feature in the calculation. So given that's happened, I got black the second time. Getting the black the second time, and did I get that? I'm just bringing it a bit higher. Black the second time now, well, there's going to be 18, but I already took out a black, so it's 7 on 18. And then black the third time, I already took out 2 blacks. So now there's 6 black left. Okay, started off with 8, but there was 7 and then 6 black left, and then there's 16 in my denominator. So the multiplication we need to do, and for space-wise, I will drag this one over here. Does it fit? No, we're just going to leave it there. That's safe. That's safe. The calculation I need to do, my multiplications are 7 on 18. And I'm going to put it in blue just so that I don't mix. 7 on 18 multiplied by 6 on 17. And that is the calculation that we require. That is the calculation we require. Just trying to be as clear as possible. This is the multiplication we want to do. The full calculation we want to do. The 11 on 18 times 7 on 17 plus the 7 on 18 times 6 on 17. Hopefully that makes some sense. We did not use the 8 on 19 in the calculation because that's the condition. We didn't have to take it into account in the model, but I wrote it down simply to help me with working out what the with my counting. That's what I wrote it down there, to help me with my counting to get the 2 probabilities that we need to multiply. That event, what I'm trying to say is is the B1. We got B1. That's given, so that's happened. It's done. It's dusted. We don't need to use it in calculations anymore. That's the idea I want to try and get home in this context, this model. It's happened. As a result of it happening, we have a new world. And that new world, in other words, and this is the other way of thinking about it, the condition, as a result of that condition, and this is probably actually, this is an easier way for you to think about the model and work on it. Given that the first ball is black, you need to take that out. First ball is black, so let's adjust. All I've done is adjust the numbers for this new reality. If the first ball is black, then you're actually building a model based on the fact of having 11 red. And hopefully this really brings it home. It's 11 red and 7 black. That's what we're thinking about, and that's what we've done. We've said, okay, it's happened. The first one was black. Pull out that black. Now I have a bag with 11 red and 7 black. I put back, and I should have said black. Okay, 7 black. And what has to happen? I have to get red and black or black and black. That's what I've done. That's the model. And perhaps that's easier for you to think of it that way. And you're probably thinking, well, sir, why didn't you just say that? Well, because it didn't come to my mind until it just came. Come on, work with me. It just came to my mind. But that's what we've done. We've created the condition has created a new situation where there's 11 red and 7 black, and we've built the model on that. Getting red the first time, 11 on 18, then getting black, 7 on 17. Getting black the first time, 7 on 18, second time, 6 on 17. So it really brings it home there. I like that. Why didn't I think about that before? It's just what happens, and probably because I want to write all this lovely set notation, but hopefully you can see those connections, and hopefully it's more concrete now by making that reference I've made towards the end there. And obviously in the end we want the calculations, and what is the calculation? The answer we should get 119 on whatever, 119 on 306. Your final answer should be 119 on 300 and 306. That's what you should have as your answer. And now hopefully you think, okay, after that moment, I am expert. They can show any funny set notation. They can talk about the world conditions, what happens 2-3 times, and you can ace it. Conditional probability, expert. More practice is required. You can never do enough practice. And maybe you should do a test as well to see what you really can do. All those things, options available to you coming up.